Most people approach a search box with a specific goal in mind, but translating human intent into the exact vocabulary required for optimal document retrieval is a mathematically and linguistically imprecise act. System architectures view your initial search as a flawed, preliminary probe, a rough estimate of intent that requires further refinement before the database can yield its most relevant results. To return genuinely useful results, the search engine has to step in and automatically modify that initial probe. This modification process splits into two approaches. There is relevance feedback, where the system uses data from known relevant documents to adjust the search, and query expansion, where the system actively adds highly correlated terms to your original string. This chart maps how systems solve the first query problem, splitting into two branches. The top outlines explicit feedback, relying on direct user actions. The bottom captures implicit feedback, deriving intent silently using statistical analysis of the document collection. Early search systems relied heavily on those explicit user inputs to train their models. Today, web-scale engines lean almost entirely on implicit signals and behavioral proxies. Regardless of the branch, the mathematical objective remains the same: taking a vague human intent and mapping it into a precise, multidimensional vector space. In a classic explicit feedback cycle, the search engine retrieves an initial batch of documents and asks the user to manually mark the top 10 or 20 as either relevant or non-relevant. The system then uses those manual judgments to execute a geometric adjustment known as the Rocchio method. This diagram shows the underlying logic. The Rocchio method physically moves your initial query vector across the multidimensional space, pulling it closer to the neighborhood of relevant documents and pushing it away from the non-relevant ones. The exact movement is calculated using this equation to produce a modified query vector, Q sub m. The middle term represents the positive feedback. By taking the sum of the known relevant documents, D sub r, the system calculates their centroid and mathematically pulls the modified query toward that exact coordinate. The final term is the negative feedback. The system subtracts the sum of the non-relevant documents, D sub n, repelling the query vector away from that cluster. The alpha, beta, and gamma variables in the formula act as tuning constants. They allow engineers to weigh the importance of the original query against the new positive and negative feedback data. Other explicit approaches achieve modification in entirely different ways. The probabilistic model recalculates the probability distributions of the original search terms without adding new terms or moving a vector through space. The structural limitation of all explicit methods is friction. Web users rarely take the time to proactively label training data for a search engine. The Rocchio method provides a mathematically rigorous way to hone a search, but the reliance on proactive human labor forced engineers to find passive behavioral proxies that could trigger those exact same vector adjustments. Web users won't fill out a feedback form, but they will click on links. Eye tracking studies confirm that users scan search results sequentially, starting at the top and heavily analyzing the first 5 or 6 links before scrolling further. A click does not guarantee a document is highly relevant to the query. Instead, it indicates a relative preference for that specific result compared to the items the user evaluated immediately before it. This sequence of scanning and clicking allows the search engine to log a mathematical preference relation. Using the skip above strategy, the system operates on the assumption that if you clicked the third result, you actively evaluated and rejected the 2 above it. It records result 3 as strictly greater in preference than both result 2 and result 1. A more conservative approach is the skip previous strategy. This asserts only that the clicked result is better than the single result immediately preceding it, yielding one inequality. By extracting these simple inequality equations from millions of individual search sessions, engines generate the continuous datasets required for machine learning at scale. These sets of inequalities are translated into an optimization problem and fed into support vector machines. The support vector machine solves the optimization problem and outputs optimal weights for the document terms, effectively generating a modified ranking function learned entirely from user clicks. By treating a skipped link as negative feedback and a clicked link as positive feedback, modern systems execute the structural intent of the Rocchio method without asking the user to do any extra work. When someone submits an entirely novel query, or the system lacks sufficient historical click data to draw from, behavioral proxies fail. This requires the final tier of our framework, implicit feedback derived through pure term analysis, split into local and global methods. Local analysis extracts feedback strictly from the text of the top-ranked documents retrieved by your current query, evaluating the immediate context of the session. To perform local clustering, the system quantifies term correlations. It creates a local term document matrix, M', representing word frequencies, and multiplies it by its own transpose to yield a local correlation matrix, C'. The C' matrix mathematically proves which terms frequently co-occur strictly within the bounds of this specific set of retrieved documents. High values at the intersection of two terms lock them together into a local cluster. These highly correlated neighbor terms are then silently added to your original search query to improve document recall. Global analysis abandons the immediate search results entirely. Instead, it analyzes the overarching statistical structure of the entire document collection. The technical hurdle here is that highly valuable, distinct expansion terms often have low frequencies across the total collection, making them difficult to cluster directly through simple term-to-term correlation. To bypass this, systems build a statistical thesaurus using the complete link algorithm. Rather than clustering isolated words, this algorithm pairs off entire documents based on their cosine similarity. It aggressively links documents together into small, tight groups, enforcing a rule where the similarity between two clusters is determined by the minimum similarity between any two documents within them. When a cluster reaches a specific threshold class, it solidifies. The engine then extracts the low-frequency terms from within these tightly bound document clusters. Those terms become permanent thesaurus classes, ready to be deployed to expand future queries. Whether applying local matrix math to a single session or building global document clusters, the system constructs a statistical associative memory, augmenting your query with critical vocabulary you didn't even know existed. Looking at the full feedback methods framework, the scale of the architecture dedicated entirely to query modification becomes clear. Modern search operates as an active, iterative feedback loop, constantly recalibrating based on incoming data and behavioral signals. It operates using the explicit multidimensional vector adjustments of the Rocchio formula. It continually optimizes term weights by extracting mathematical preference inequalities from user clicks, and it executes deep matrix algebra to cluster documents and map global term associations. All of these distinct mechanisms serve a single goal: bridging the semantic gap between human linguistic equestimation and algorithmic precision. In information retrieval, the first query serves as the initial input for a self-correcting computational engine designed to find precision